Okay, second talk by Tschinkel. The title is on the first slide, Equivariant arithmetic geometry.
Well, I'd like to thank the organizers for giving me the opportunity to speak at this celebration for MG. So my work is in number theory arithmetic. It's not quite related to reflective geometry, but I hope that the talk will show you at least some instances where ideas from arithmetic do have some impact on geometry. So there's a picture of Kenji drawing circles and squares. And, well, I draw circles and squares. I looked up some of his papers to see whether or not there are other connections to the kind of work that Kenji does, and maybe I'm interested in. So nilpotent structures, toric degenerations. Yes, toric varieties. So the plan for the talk today is to look at, well, unipotent, nilpotent flows, look at questions concerning rational points, then discuss birational invariants and toric degenerations and rationality. All right, so squares and circles. Basic problem is to count lattice points in some expanding domains, for example, circle. And the basic observation is that frequently you can compute the volume, and the volume will give you asymptotically the number of lattice points in the domain. And then there is some error term, and then the game is estimate the error term, compute the volume. And of course you want to show that the error term is smaller than the main term, because otherwise. Now, so this is related to counting rational points on P1. So you represent the rational point by a pair of integers, co-prime. So then you're counting not all lattice points in a circle, but only some, where the coordinates are co-prime. You pick your favorite norm, square sum of squares, and then you look at the number of points of bounded height. And well, pi r squared, this is what you expect, the volume. But because of those corrections, you look at co-prime entries, you're seeing some correction factor, 1 over zeta 2, and then 1/2, because plus minus 1, okay? Now, what is this 1 over zeta 2? So let's write this in the following form, 1 plus 1 over p, 1 minus 1 over p. And then let's think of the first term there as simply the number of ft points on p1 divided by p. This is some kind of density. And then there is this correction thing, 1 minus 1 over p, that we'll explain later. So this can be interpreted as a certain volume on the adelic points of p1 with respect to some very natural measure, which is regularized by this factor 1 minus 1 over p at each place. All right, so that was P1. You can also count points of bounded height on cubic surfaces. For example, this one, the E6 cubic surface. I've plotted some of the rational points. You sink a ball, and then, well, how many points are there? And the answer is b log b to the 6 this time around. There is a leading constant, which has this form. It's a product of three things, alpha, beta, tau. Alpha is this big rational sink. Beta is 1. Still, it has a place here because it's not always 1. Sometimes it's the order of H1, some Galois cohomology groups that's naturally associated with Galois Ekstrom Picard. And then there is a Tamagawa number, and again, it's something that you compute, and it's a number of FQ points, FP points on the cubic surface, divided by p squared, p to the dimension, regularized by 1 minus 1 over p to the 7, and the 7 is the rank Picard of the cubic surface. And then there is something there on the reals. It's some integral, and it turned out that this integral is actually the same as what we're computing in finite places, except that, well, that's what it is. Again, you can look at other things, and all I want to say is that there's a huge industry now counting rational points on surfaces, on high-dimensional varieties. There are conjectures that describe these asymptotics. There are many people working on this. So the framework for everything is Manning's conjectures. You look at varieties which hopefully have many rational points. For example, Fano varieties. They have many rational curves, well, therefore maybe many points, arithmetic analog of that. And they have some distinguished embedding, and then you can say, well, let's count points of bounded height on this embedding. And then the conjecture is that it's going to be b to the 1, log b to the rank Picard minus 1. Okay, in general, it's not known that Fano varieties even have, potentially the risky density of rational points. So even in dimension 3, there is one case that's open. But we can start from the other end. We can start with varieties that a priori have many rational points, and those come about when you look at the group actions. Your favorite groups tori or linear algebraic groups. You look at rational representations, you get an orbit. We can look at very special representations, for example, where the orbit is risky dense. Okay, so those have been studied, like Sato, pre-homogeneous vector spaces. Well, but there are many others. And so the setup then is you look at this algebraic flow. Now you can think about projective representation, so acting through PGLM on some projective space, or acting on the affine space. With GLM it doesn't matter. So in one case you look at rational points, in the other case you would look at integral points. You look at the flow, you pick a ball in your space, your favorite norm, and then you ask yourself, well, what's the asymptotic? Now, again, there is a framework that explains all of that, and there are many results for rational points. I've been working on this for many years with various co-authors. So essentially, whenever you give me some group or homogeneous space for that, after a lot of work, the original conjecture that I formulated, Mellin conjecture, holds. So whenever we look at some equivariant situation, be it semi-simple or unipotent or anything that we laid our hands on, the conjectures hold. But there are counterexample in another context. Sorry? Oh, no, it's rational points over non-closed field, over Q, over number field. Or function field, FQ of t. There are results in this direction as well. No, this is a purely arithmetic thing. You look at lattice points in balls, so you need arithmetic. It's really lattice points. And then there is also an industry looking at integral points where you act through some GLN. So, and then there is some integrality property, and again, and there is a framework which interpolates between rational points and integral points. Now, what I want to talk about is volumes. Okay, volumes, how do we compute these volumes in the first place? Not in all cases can we show, in fact it's wrong in some cases, that the asymptotics for the volume balls, the volumes of those growing balls, approximates the number of lattice points inside. That's not the case, strangely, and there are plenty of examples. Nevertheless, you would want to compute such a thing over the reals, over the complex numbers, and also over the p-adics. So, and as I'm writing here, the difference can be a constant factor. Well, this would have to do something with weak or strong approximation. Not all congruence classes are hit, for example, for some reason. But sometimes even exponents are messed up. The log power is different and so on. So, how do we compute volumes in these kind of problems? So I wanted to give you a very explicit example. 2 by 2 matrices, and I fix the characteristic polynomial, let's say x squared plus 1. And I pick a norm, like square root sum of squares, so an A, B, C, D. And then I ask myself, well, what's the volume of the height ball? And so there is a closed formula. It's C times B, and the constant C is this thing that has these common factors in there. Now, okay, and in this case, the number of lattice points is approximated by the volume. So we can look at the other case where now n by n matrices, and we fix the characteristic polynomial without specifying it. And again, we pick some norm on the matrices, square root sum of squares of all the entries. And then we can ask, well, what's the asymptotic? And the asymptotic, well, here for the lattice points is, okay, b to the m, the volume, and there is some constant. So there is a theorem by Modular from 2004 that you take any semi-simple real Lie group, Haar measure, vector space, representation, pick some norm, compute the volume. Okay? And the answer is b to the a log b to the b minus 1 with some constant. And a and b, as you can imagine, they're defined in terms of combinatorics. Root systems, real roots, this, that, and the other, some combinatorial things. Moreover, so you compute the volume, right? There's some leading term, b to the a log b to the b, and then there's a constant in front. And what's this constant? And Modular shows that this constant, it can be computed as some kind of residue, as some kind of integral over the boundary. So you look at some kind of G pi equivariant submanifold and that's where your measure is localized, and the volume of that thing shows up in the constant C. So the proof is representation theory, no geometry. It's just so. Now, in the context of algebraic groups, especially semi-simple groups, you can, in principle, reduce everything to combinatorics. But in context of cubic surfaces and other things, there are moduli, no combinatorics is available. You want to have a geometric explanation and hopefully geometric proofs. So, what was open, therefore, how to compute these height poles in analytic and adelic setup in sufficient generality, big generality, and generality that would be applicable to, as I said, Lopezzo surfaces, but also to algebraic groups. Now, and then you want to use this to maybe study asymptotics or the number of rational points of bounded height and things like this. All right, so heights, we have some variety. It sits in projective space. We have rational points. And then there's this notion of metrized line bundles, adelically metrized. So if you've never seen such things, the previous examples give you sufficient intuition for that. You just fix some integral models, so equations have coefficients of integers, and then you take your rational points are represented by integral vectors, and then maximum of the coordinate, something like this. So then you have a height, so positive real number, and then you do something with it. Now, the height is it's an adelic and metrized thing. So you have local height, so your line bundle over the p-adix is metrized. So you can use this to produce measures. Okay, so we start with metrized canonical or anti-canonical line bundle. You pick local analytic coordinates and the p-adic points, real or complex points, and in some neighborhood of a point, and then pick some local section, and the measure is simply the norm of that section times the standard, let's say, normalized Haar measure on the affine, the v-adic points of the affine space. Okay, so this is a local thing, and the beauty of this is that you change coordinates. When you do the passage from one chart to another chart, things cancel appropriately. This thing globalizes over the p-adic manifold. So this is called the Tamagawa measure. So it was known before Peire in the context of linear algebraic groups. It's explained very well in the book by Andre Weil. And this is how you produce Tamagawa numbers on algebraic groups. And the advantage in that context was that you have some kind of canonical metrization staring at you, and typically it's explained as well, pick a top dimensional differential form, top degree differential form. Once you pick it, then you can define this and the other. What Peire realized is that it has nothing to do with algebraic groups. It works whenever you have a metrized canonical anti-canonical line bundle, you have such a thing. Okay, so, and then the observation is that when you do this and you integrate over the v-adic points of your variety, which is a smooth projective forever, what you get is the number of q points over q to the dimension. Now that's beautiful. So this is how you get, in my previous slides, p1 of fp, yeah, showed up as some kind of integral, p-adic integral. So this here is a formula that's very easy to prove. Weil did it in the context of linear algebraic groups, and Peire took that proof and transplanted this into geometric setup. First applications. So this was 95. So Victor and I were working on toric varieties, counting points on toric varieties, and you see what you want to do is do harmonic analysis on the torus. So the answer is you get some data functions, leading term, it's some integral over the torus. But then Peire tells us that the asymptotic should be an integral over the closure, and it's going to be fq points on the closed variety. But you're integrating over the torus. Well, how is that? Well, it turns out that you integrate over the open part, but the answer is fq points on the whole. So Victor at that time was thinking about Calabi-Yau's, and he realized that immediately you can prove that birational Calabi-Yau's have equal Petty numbers. How do you prove it? Okay, you take this Tamagawa measure that Peire defined, you integrate, you get the number of fq points. Now, Calabi-Yau's have a, trivial canonical class, so there is a canonical metrization on that. Okay, you take that thing that's given to you, you integrate over some Zariski open subset, you have birational ones, they have the same Zariski open subsets, and the integrals don't depend on the completion. So, well, that's wonderful. In one case, you get a few points on one variety. In the other case, you get a few points on the other variety. You get it for all q's. Okay, then use Weyl conjectures. So, okay, Maxime generalized it vastly. The motivic integration came from there, and many other things. But that was kind of the first instance that came out of pure number theory. Now, let's continue. So this was local. But in our counting problems, we have the Deluxe picture in place. And so what typically happens is that the local integrals converge. But the Deluxe is there's some divergence. This happened already in Weyl. So what you need to do is you have to regularize in a systematic fashion all those local contributions. What does it mean? When you have an Euler product that starts with 1 plus 1 over p, you don't want that 1 over p. An Euler product that has 1 over p is a divergence. So you try to kill systematically all the 1 over p factors in your sink. Well, what is that? When you look at the Weyl conjectures, it's, well, the piece that's sort of h2 or h minus 2, and, well, that's a Picard. So what you want to get rid of is Picard group contribution to the Euler product. So you regularize by, well, the RTNL function. Picard is a gamma module, so, okay, the local contributions change from place to place, but in some very systematic fashion. So once you regularize by the local factor of the RTNL function here, then you've eliminated all the 1 over p contributions, the thing converges. So it converges, and then you have to put it back in. And how does it happen typically in arithmetic geometry? You put back the residue at 1. Your L function has a pole of some order, and you put the residue at 1, and that's... So you get a regularized Deluxe measure, and then Bayer introduces this constant, this integral over the closure of rational points of the dells. Forget that for now, but just take integral over the dells of this Tamagawa measure. And that's a constant that shows up in all the asymptotic formulas in minus conjecture. Okay? So in over P1, over cubic surfaces, compactifications of groups, that's what it is. Now, so let's go back to height poles. We have, you know, the following general question. We pick some effective dividers, look at the support, and so here F is a local field, p-adics, real complex numbers if you like. So you have a height pole. Okay? Now, we want to compute volumes of these height poles. So think of that as you get into some embedding, you know, and then in that embedding you have some growing ball and you want its volume. So the idea is that we compute this using Mellin transform of the measure. And I'll show you in a second how it helps. So let's look at, so we have this divisor D, the support of our line bundle, and we can assume it's normal crossings, union of some things. So there is some stratification of the boundary, so stratification, you know, intersections of these divisors and open pieces. In the stratification, there is some transversality assumption. Now, we can write our divider in terms of, well, anyway, we write our line bundle with coefficients along these components, and then it turns out that if you want to compute the Mellin transform, so your height pole can be understood as some kind of distance to the boundary. The boundary has these dividers there, and you look at, for each divisor, distance to its divisor, and you compute essentially, well, it's a singular measure, but you can measure the amount of singularity, so there are some complex numbers here, there's some complex number S, and you want to understand the meromorphic behavior, analytic properties of these kind of integrals. Now, the beauty is that, well, you compute these integrals in charts. Just real complex numbers, you put charts, and in each chart you only see kind of one piece of the boundary. either a divisor or intersection of divisors, and then you just simply work in those charts. And that allows to reduce these complicated looking things to essentially products and sums of integrals of this kind, where you have simply one coordinate, that's x, that's your distance to the boundary, and you're looking at the integral x to the s, or x to the minus s, and that's what you're computing, and you want to know, well, where does it have a pole? And what's the residue at this pole? Well, for this kind of integral, we certainly know how to do it over, real p-adics and so on and so on. And the beauty is that once you put it in this way, you know exactly where the first poles show up, and there is an abscissa of convergence for this thing, which is obtained by kind of convex optimization problem. You have to compare coefficients, and then you know what the order of the pole is. It's some kind of polytope, and you're looking at what's the face of this polytope, and then you get the leading coefficient, which is a sum of contributions over strata which contribute to this pole. You may have seen this in the things that you do. And now when you want to do it adelically, then you split everything again into these local integrals. But now you need to understand the picture uniformly. And here comes a thing from a little bit outside, which is this de Neuf-Lazare formula. And the de Neuf-Lazare formula, it's a refinement, if you like, of Perez formula, which was counting fq points, x of fq over q to the dimension. Here, we get a formula, it's a sum of all boundary strata, and in each boundary stratum, it's a product over sort of divisors contributing to this boundary stratum, and then q divide minus 1 over q to the s alpha minus rho alpha, which is the multiplicity, the canonical line bundle of the stratum, plus 1 minus 1, and then there is this sum number of q points over q to the dimension. So please stare at this formula because it will come back very soon with different applications. So how do we interpret this? Okay, just imagine this thing is 1. So q minus 1 over q minus 1. Imagine this thing goes away. Then what are we seeing if you're not seeing this? We're seeing sum over all strata of fq points in the stratum over q to the dimension. Well, that's exactly the number of fq points on the whole thing. That's the Tamagawa type integral that I showed you before. So you should think of this formula as kind of refinement of Wales-Perez integral. Now, this already is very useful because, well, this is how we regularize and understand the poles of the Euler product that is staring us in the face. While at each individual place, you get some strange things. You see, when you work arithmetically, at almost all places, it's fixed, it's this. And so all the poles come from the Euler product. And then you just stare at this. It's a arithmetic combinatorial thing. Which components contribute to the Euler product? Well, 1 over q. Well, how do you get 1 over q? Well, this A consists exactly of one thing, namely divisor. So what are you seeing? You're simply seeing, for each divisor, you're seeing some kind of contribution. And so now, in arithmetic, okay, from place to place, the stratification can change. You see the Galois group, your components don't have to be reducible of the ground fields. There's some kind of Galois action on components and so on and so on. But you can organize all of this in a neat fashion and regularize by an appropriate thing that's in Galois representation that you understand. So, okay. And these are the kind of things that allow us to analyze this Euler product. We know where the poles are. We know what the leading terms are. And the leading terms are, well, you take this Tamagawa thing. I showed you how to regularize this. So it's well understood. Now, so let's move on. And then you use some Tauberian theorem to convert information about these Mellin transforms, the data functions that I worked with, into asymptotics of height poles. So in other words, you give me anything algebraic, and I can compute these hyperbolas for you. I can compute integrals for you in some closed formulas in this way. Okay? So whenever you have something, some function f of x, absolute value, you want to integrate this over something algebraic, so this formula will apply. It will do it for you. Okay, so that can be used. So a sample problem, unipotent groups, nilpotent. if you like. Let's look at some compactification. Okay, projective variety. G is sort of Zariski open subset in it. The boundary is a union of these strata. G equivariant resolution of singularities allow you to assume that it's normal crossings. Everything is nice. We want to count rational points or integral points, it doesn't matter, on the group. And so what do? We introduce a height pairing, which is now, again, kind of for each divisor, you look at distance to that divisor locally. And then you simply take a product over all these things with weights, complex weights. So previously we had sort of one complex variable. Now for each divisor we have a complex variable. So we live on the complexified Picard group, which is, in this case, really spanned by the classes of the boundary components. Okay? So we have from C to the rank Picard some kind of pairing between the delic points and divisors. And okay, locally it's distance to the boundary, and then you take a product. Now, so the height theta function is sort of the analog of what we did before for these volume asymptotics. You sum over all rational points. It's a generating series. You need to understand its analytic properties. You have to find the first pole and compute the leading term at this pole and the multiplicity at the pole, and that will give you asymptotics for points of bounded height in these drawing balls. So how do we approach these things? Well, this is now Fourier analysis, and in this case, if the group is non-abelian, it's going to be non-abelian Fourier analysis. We look at some spectral expansions in L2, and then we analyze each term. We need to show that everything can be summed and so on and so on. But where is the main term? So the main term comes from the trivial character in this case. And what's the contribution of the trivial character? Well, you integrate your thing with the trivial character, with 1. So this is a height integral over the Adels of exactly the same type that we looked at before. So we know what the answer is. I suppressed here the contribution at infinity, but at each finite place, you're seeing the whole formula that we understand. So it has poles where this thing is 1, that's where you get the pole, and we know the leading term, and this way you prove Mellin conjecture for these kind of compactifications. Now, there is a lot of work in trying to control the error terms in this expansion. So here we had to really learn about the orbit method of Kirillov. We had to write down explicitly all those expansions, estimate integration by parts, this and the other. A lot of messy work, but the idea that Mellin's conjecture can be proved and is true, it's on this slide. Now, so in all that work, there's always this sort of tension. How much arithmetic is in geometry, how much geometry is in arithmetic, and I have to tell you that both points of view help a lot, because when calculating, and like in this business, you make mistakes all the time, but these two sides, it's so rigid that you can't make mistakes somehow, because if things don't fit, then, well, they have to recompute. So this is very structured part of arithmetic geometry. Well, now, and so how much geometry can be read off from arithmetic? So now I'm going to switch gears and talk about something totally different, nothing to do with number fields, just complex algebraic varieties and the basic classical question, which one is rational, which one is not rational. So rational means birational to projective space. Stable rational means you multiply with projective space, you have a rational projective space. Unirational is you're dominated by projective space. Now, in dimension 2, complex numbers, so in dimension 1, it was no classically everything that you want to apply. Unirational, stable rational, rationals are all coincide. And the way it works, essentially, it's MMP for surfaces. You just classify basic transformations that you can do with surfaces, exceptional curves, contract, there are basic things. P2, P1 times P1, that's it. Now in dimension 3, things are much more subtle, and well, they were counterexamples to there are unirational varieties that are not rational based on different things. For example, birational rigidity. You look at birational automorphisms, intermediate Jacobians, the Clemens-Griffiths method, and the Brouwer group, the Arts and Mumford example of a conic bundle over a rational surface. You compute the Brouwer group. It's birational invariant. It's non-trivial. And then there's more recent work that stable rationality does not imply rationality in dimension 3. It uses intermediate Jacobians as well as a method developed by Lang and Sansuk called the method of universal torsors. I spoke on this on other occasions. I won't go into this now. So there's been sort of dramatic recent development in this story, started by Voisin, namely understanding stable rationality and the failure of stable rationality via degeneration. So what typically happens is that you look at your favorite variety, like a quartic threefold. And, well, it's rationally rigid, it's not rational, but maybe it's stably rational. How do we know it's not stably rational? So that was open until very recently. So the method that I'm about to describe in more detail goes like this. You start with, you look at the family of these varieties, and if you can find that in this family, a mildly degenerate fiber picks up some invariant that's non-trivial that you haven't seen before, some abstraction to rationality or stable rationality that you haven't seen before, then there's a way to conclude this for a very general member of the family. Conclude the failure of stable rationality, for example, or rationality. So Voisin demonstrated this with a very specific example, but she really started this whole thing. People came up with different versions of the specialization method. In particular, in 2017, he says in Schindler, they showed that directly, without the initial approach via zero cycles, theory of Bloch and Srinivas, that stable rationality specializes in the family where the special fiber is mildly singular. So the advantage is that, as I said, the smooth fiber need not have any obstructions to rationality or stable rationality, but often you can degenerate into something mildly singular that picks up a non-trivial Brauer group, for example. And that's an abstraction to stable rationality. And then you conclude that same property for the family. And Maxime was visiting New York. We started looking at this paper, and within a day, we realized that what Nikas and Schindler were doing in the context of, well, K0 varieties, complicated. Anyway, so that it actually works directly. We showed that rationality specializes and birational types specialize. And so let me explain this in a little bit more detail. So there was some initial work of Larsen and Lunds to the effect that you look at K0 varieties, the quotient out by the class of the affine line, and that is actually isomorphic to free abelian groups spent or generated by classes of algebraic varieties over your field, modulo stable rationality. So what was essential in that initial paper was that so there was this weak factorization theorem that showed that birational varieties can be linked via a chain of basic operations, blow up, in smooth centers. Very basic steps. Because before that, birational is rather complicated thing. Now, okay, so there was this result, and Nikas and Schindler realized that there is this kind of motivic reduction formula, came out of motivic integration, that allows to produce a homomorphism from K0 varieties over the functional field generic fiber and special fiber. So this is very much inspired by the motivic integration as developed by the Neuflaser, so after Maxime's. What we then did following Nikas and Schindler is to simply forget about stable rationality. Look at the abelian group spanned by rationality classes. And then write down a formula that will be the specialization formula, but in the context of this other group. And what's the formula? So you start with your variety, let's say, with the Laurent power series. And then you have something called the generic point. You spread it out. It's an integral model. Okay. And then you write the thing in the special fiber, again, as union of components. Okay. Again, there is this stratification. And then you need a formula. Now look at this formula. It's essentially the same formula from before, except that now we're not integrating. There are no FQ points here in the picture. We don't care, just things. So what was crucial? You see, when you do these periodic integrals, as I was stressing, you're integrating over the open part, but the integral picks up contributions from the boundary.
Sorry, where does this equality take place?
This is in the Burnside ring that is the three abelian groups spanned by classes of birational things. So that's, you can look at this for the generic fiber, for this field, and then for the special fiber. So this is, you produce a net like this. So, now, okay, forget this relative picture, integral models, just think in absolute terms. In absolute terms, you have something open and you have a boundary. And you want to say that I can do something, pick some invariant from the open and move it to the boundary. Well, this is what we're doing. Integrate over the open, get sum of contributions from the boundary, plus minus, plus minus. All right? So now spread it out. You have something over the generic fiber. Now your boundary is the special fiber. So you're integrating, so to speak, over the generic fiber, and you're picking up contributions from the special fiber. This is what we're seeing. And then, what you need to show is this doesn't depend on models chosen, this, that, and the other. But different models differ by these birational transformations, and all of those can be factored as a weak factorization, where you really control, you know, the blow-ups at each stage. And so then you just need to compute that when you replace this formula by a similar formula for the blow-up, kind of one of these standard blow-ups, nothing changes. And the formula is designed in such a way that nothing changes. So the perspective of integration is obvious. As I told you, you integrate, you don't care what the boundary is. The integral will be the same. So now comes the thing. Maxime told me this morning that I should also discuss some works that we were doing yesterday all day, as well as weeks ago. So, okay, so this is very recent. And it comes from the following desire. So I will show you later that this previous formula, you see this kind of thing, allows to understand rationality type. Okay, so it allows to prove rationality, specialize various things about rationality. When you do minimal model problems, algebraic geometry, or arithmetic geometry, you frequently have to deal with groups, finite groups acting. So before I told you Gallo group could act on your thing, right, on your boundary strata, you know, can split. Anyway, it's very natural, and there is actually a big industry out there to study birational geometry in the context, in the presence of finite group actions. There are many, many papers, Prokhorov, Cheltsov, many others who look at interesting threefold, singular Fano threefolds with all kinds of symmetries, and trying to prove is this equivariantly birational to that. Now, already understanding that one three-dimensional variety is birational to another three-dimensional variety is a huge headache, because to explicitly produce these birational things is a nightmare. And in fact, there are many examples, linear representations, for example, your favorite group PGL2F7, four-dimensional representation, projective-wise, it's unknown whether the quotient is rational. You know, simple things in dimension 3 already in presence of these kind of group actions are very hard to understand. So understanding equivariant factorizations, equivariant birational geometry already in dimension 3 is very, very hard. So it would be nice, was the idea and the desire, to have some tools that would allow to do G equivariant, let's say, specialization. And so that's how the discussion started. And then we realized, wait a minute, we don't even understand the absolute case. Forget that model, forget that specialization. Just look at the absolute case. You have one variety, you have another variety with G action. So what kind of invariant can you write down? So let's say you have a abelian group, even a cyclic abelian group, Z mod P. Now, let's look at the variety with an action of this group. And, well, it's a birational action, but you can do equivariant blow-ups. You can assume this is actually regular. And then you can look at fixed point for the action, so fixed loci. And you stratify this. I mean, it's a union, disjoint union of some strata. And then in each stratum, you can look at the action of your abelian group in the tangent bundle. So you pick up some characters, okay? So characters, elements in the dual abelian group. So let's keep them. Let's just have them in front of us. And that's what's here, so characters. And my invariant is going to be simply, let's take variety, and let's just push it and express it like this. Now, and then let's forget f alpha for a second. Just pick up the characters, and, well, we have something, some symbol. Now, what do we want? We want an invariant. Therefore, you look at equivariant blow-ups, and we want that these expressions don't know about the blow-up. In other words, the difference between this and this is 0. So introduce these symbols and impose these relations. So this is what happens. So relations are labeled by the dimension, so n. Symbols are these, a1, an, ai are in the characters of your abelian group. And, well, because you don't, I mean, in your tangent bundle, you don't know what the order is of these eigenvalues, of these characters. You don't care. There is this symmetry property up to permutation of the entries. And then there is this thing, which is a kind of an equation that I'll explain an example in the next slide. Okay? So, now, of course, well, it's an invariant, but sometimes you have no fixed points whatsoever. Well, then you don't see anything. Okay? So, the statement is that this thing is a well-defined G equivariant birational invariant. So, what does it mean? This formula that I wrote down, modulo those symbols, is invariant on the blow-ups. That's how it was discovered in the first place. Now, what is this in dimension 2, or if you like, codimension 2, for n equals 2? So there are two things, A1 and A2, in D mod P, not both 0, and the property is symmetric. And then you have this kind of equation for the symbols, and that kind of thing. That's it. So now you can ask yourself, all right, so these are my relations on the symbols. Let's see what we get. So how many linear equations do we have? How many variables do we have? The variables are pairs, A1, A2. And you look at equations, and the number of equations in this case is the same thing as the number of variables, but the dimension is p squared, if we look at D mod P, plus 23 over 24, numerically. You run it for the first couple of primes, this is what comes out. Then you wait a minute. Then you start playing with the symbols, and you realize sometimes you have torsion. You have 2 times the symbol equals 0, implied by the relations that I wrote down. Well, you're not surprised if there's 2 torsion. There's plenty of 2 torsion. But there is, you know, at 37, torsion in 3 and 19. And then, you know, computer begins to produce more and more results. For n bigger than 3, the system of equations is highly overdetermined. So the number of terms, variables, grows like p to the dimension. So if you want to work in dimension 5, and your prime is up to 100, so it's 100 to the 5. Okay? It's a very, and then many equations. They're linear equations, because they're just linear equations on the symbols, right? So here are the equations. So it's a very sparse matrix of huge dimension, and you want to compute its rank. So, okay, you compute the thing in dimension 3, and you get p minus 5 times p minus 7 over 24. You say, wow. And then, that's what you get for the first couple of primes. You say, wonderful. But then the computers begin to get hot, and suddenly you get an extra dimension for 43, 59, 67, 86. What is going on? So now, when we saw that 24 from such a simple thing, well, if you get a 2 in the denominator, that's okay. How do you get a 3 into the denominator? So there is something called modular symbols in the theory of elliptic curves, or modular curves. So they're generated by symbols. So these are symbols. CD, well, CD because there is A, B, C, D. CD is sort of the lower sink of a matrix. And again, Z mod n, subject to relations of this type. Well, this, for example, shows that the symbol is sort of not symmetrical. And our symbols are. But this thing with minus C minus D, well, it's almost like our relation, except that in our relation we had C minus D, and here there's minus C minus D. So things don't quite match, but what is known about these modular symbols is that the dimension of space, well, these symbols, there is some, anyway, so there is some boundary map. You look at symbols, boundary, there's no kernel of this boundary map, and that's dual to modular forms, weight 2 for gamma 1p, and the dimension can be computed, and that's the dimension. Now, this is what we found as a dimension of B2, of Z mod p. And this is the dimension of B3, of Z mod p, except that there are jumps sometimes. So then, big computers come into the picture. Here's dimension 4, and you can look at the jumping. For example, here at 43, for n equals 4, rank is 1. While for all other primes before that, rank, the Q rank, is 0. But as for 2 torsion, that's displayed here, as you can see, huge variation in 2 torsion. So this is clearly a very rich structure that emerged here. And, well, so this is what is happening in the paper that is in the process of being written or finished. There are groups on these symbols with slightly different a priori relations. On those, there are some Hecke operators. The slightly different thing is actually the same as this thing, conjecturally. We produce a homomorphism from the birational group into these things that we call modular thing. The Hecke operators are the modular thing. We conjecture that they're isomorphic, so they get Hecke operators on the birational things. Then you can study a spectrum of these Hecke operators. It's a big commuting rational operators. And then there are some experiments. You see distribution of eigenvalues, so it's a very pretty picture. Then you can look at non-abelian groups. I mean, after all, you have a finite group, you have a fixed point locus, or even, where the stabilizers begin to jump. You just have to keep track of that whole picture to produce more refined birational invariants. So this is very much kind of an open thing, but
what are the simplest examples of variation in G-naught?
the interesting examples of what?
Variation and not equivalent, G-equivalent.
So, okay, so let me give you an example that I consider interesting. P1, with the action of Z mod 5. So, there are 2 fixed points, 0 and infinity. It turns out there are 2 actions. In one action, the weight is 1 and 4, and in the other action, the weight is 2 and 3. In this group of symbols, there are no relations in dimension 1 whatsoever. So the sum 1 plus 4 is not equal to 2 plus 3. So that shows that P1, this is the 5 action, has 2 different, not equivalent things. So you can soup up this example.
These 2 or 2?
2. That's what, for Z mod 5. For the other groups, you get more, Z mod 7, but not for Z mod 3. Now, you can soup up this thing, you can come up with a rational surface. There's an action of the dihedral group D5, and another action of the dihedral group D5, different representations of D5, where, again, using this kind of invariant, you can show that they are not equivariantly birational, but they're, of course, birational, just not equivariantly. So it can be used, but using the full strengths, for example, we notice that in dimension 3, the B3 of Z mod 11 is one-dimensional. So for some reason, Z mod 11 is an interesting action in dimension 3. Okay, I haven't seen that anywhere in the rational literature, but it just comes out of these things. So now, so that's that. Now, my previous talk continues, the one that was prepared before today. How these specialization things are applied. They're applied in three-dimensional and higher-dimensional geometry, study of varieties that are close to Fano varieties, rationally connected varieties. There are many, many results by various people looking at favor of stable rationality. So the punchline is that in dimension 3, stable rationality is essentially settled, except for things which are birational to a cubic threefold. For all other varieties, we essentially understand stable rationality. So that's a combination of various things. First, Brandon and Andrew Crash, we did conic bundles. Then we did Topetzo fibrations, and we looked at Fano threefolds. And so Krylov-Okada contributed also to Topetzo fibrations. Anyway, stable rationality for threefolds is more or less done for general families. Then we can look at well, what happens in families. There was a big open problem in this rational geometry. Can rationality jump in a family? And well, okay, there was this counterexample by Brandon Hassett, Arina Perutka, and myself, where we used the specialization method to show that the very general member is not stably rational, but the rational members are dense based on some kind of arithmetic considerations. And now I'm coming to things that I've seen also Kenji is playing with, circles, triangles. So this is actually the generation locus of a quadric surface bundle over P2. So it drops rank along 3 lines on P2 by 2, and on the circle it drops rank by 1. And this configuration, that quadric surface bundle over P2 has non-trivial Brouwer group, it turns out, and the singularities are sufficiently mild. So the specialization method will say that every quadric bundle that specializes to it, or every family that specializes to it, has the property that things are not stably rational, very general things are not stably rational. There are many more examples that I will skip now, but you see, so over the complex numbers, we understand the picture, but I am kind of arithmetically inclined. I would like to understand what happens over non-closed fields. And over non-closed fields, in case of Topetzo surfaces, all of the arithmetic is essentially in the action of a finite group on the Picard. This is what is twisting the whole picture. So that's why, a subgroup of a Weil group of E6, E7, E8, to me, beautiful. This is the kind of symmetry that I want to understand. You have such things. You want to study equivariant birational geometry in dimension 2. That's back to Mani and many others. That's kind of tricky. In any event, you find obstructions to rationality over a non-closed field of geometrically rational surfaces in these kind of Galois actions. Then you can say, oh, well, what happens in dimension 3? We now understand the non-rational Fano threefolds over the complex numbers. But there are plenty of rational Fano threefolds over the complex numbers, which need not be rational over the ground field. If that's the case, what would be the abstraction to rationality over the ground field? In case of surfaces, the Topetzo surfaces, we basically know that it's Galois cohomology on Picard. But for threefolds, well, okay. So we started looking at this with Brandon Hassett, and well, the first place where you look is toric threefolds, Fano threefolds. Now, so rationality of tori over non-closed fields, that's also an interesting thing. There is also a finite group in the picture, namely, it's a subgroup here of GL3Z. That's a group that can twist your torus over a non-closed field. Of course, tori are rational over a closed field. And it turns out that in dimension 2, all tori, no matter how twisted, are rational. But in dimension 3, they are non-rational tori. And that corresponds to, well, simply looking at the biggest group that shows up is order 48. So you look at all possible subgroups of your thing. It's like S4 times S2. And okay, then you try to understand Galois cohomology for that action that presented to you, and Kuniavsky did it, and they're all classified, and I'll show you what is necessary, so to speak. And then you can look at toric Fano threefolds. But now you realize something really funny. because you see toric Fano threefolds, they have very special fans. And the symmetry group that allows you to twist your torus so that it becomes non-rational is not compatible with those fan structures. It's an easy observation that actually toric Fano, smooth toric Fano threefolds are rational. While of course, since there are non-rational tori, you can compactify them somehow, you'll get a toric threefold that's not rational. But the smooth Fanos happen to be rational. Anyway, you can look at M06 bar. Misha likes these things because he looked at M0N bar in great detail. So anyway, so there are non-split forms of that. You can twist these things and get non-rational M06 bars of a non-closed field. Okay, now, so here is the target theorem that if you have a non-toric, geometrically rational, smooth Fano threefold, which is general in its family, then it's not stably rational. Over the ground field. So here comes now the issue with, let's say, Voisin's method. In Voisin's method, if you wanted to apply it to a situation of geometrically rational varieties, you would fail. Because what it says is that you have this family, and you have to exclude the countable union of things where on the base that come from existence of cycles somewhere upstairs and so on and so on. But, so over a closed field, you know that it's going to be a finite union of proper subvarieties. But over a non-closed field, because you see all the points on the base correspond to varieties that are geometrically rational, everything is dominated. Every point on the base is going to be in the image of one of these special things that allows the rationality construction. Well, you can't really control. If you look at rational points on the base, things are coming from upstairs. Upstairs, you could have non-rational points that map to rational points. I mean, you can't control this. So the only way to play the specialization method is to use actually the theorem that Maxime and I, or Lisa Schindler proved without reliance on these things. Now, I said this is a target theorem. Our favorite example, of course, is the intersection of two quadrics and P5. Now, you look at this, there are no Galois-theoretic invariants that are available because, well, Picard is Z. No Galois actions there whatsoever. It's a Fano threefold. Picard is Z. Intermediate Jacobian, well, what is it? You know that you can fiber this thing over P1 if you assume that there is a rational point, with fibers quadric surfaces, which is the generating, there are 6 variables in the picture, in 6 points on P1. So over the ground field, you get the genus 2 curve, double cover of P1, where you split the quadric. Now that's a hyperelliptic curve, and the intermediate Jacobian is the Jacobian of this curve. So there is a Jacobian. The Jacobian criterion, failure of rationality, is not going to apply. The intermediate Jacobian is the Jacobian of hyperelliptic curve. So what on earth is going to tell us that we think is not rational over the ground field? So this is what you wanted to understand. And so we look at the field C of t. So now over C of t, you have a 3-dimensional thing, which is a quadric surface bundle over P1, which means that you have a quadric surface bundle over P1 times P1. And where does it degenerate? Well, it degenerates in the curve of by degree 6, 6, which is this, which you like as well, a square and a circle. So, which means that you drop rank by 2 on the square, and you drop rank by 1 along the conic. And now it's very similar to the previous example. This thing is not stably rational over the complex numbers. If it's not stably rational over the complex numbers, it can't be rational over C of t. Because if it were rational over C of t, the total space would be rational as well. So that's how we prove that this thing is not stably rational over C of t. At the same time, it is of course geometrically rational. How do you prove geometric rationality? A quadric bundle over P1, well, there is a section. Okay, if you have a quadric as a point, then you project, it's rational, no question about it. So that's one way of doing this, and again, you need to be able to compute the unmodified Brown group, and then also analyze the singularities, and in this case it can be done. So, toric degenerations. It turns out that this thing can be degenerated to a singular toric intersection of two quadrics. So let's see how it goes. Let's take P3 and blow it up in our favorite points. Boom, 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 boom. And you get this. So this is a toric variety, clearly, because each equation, one monomial equals another monomial. It's an intersection of two quadrics. It's singular, toric, threefold. Now, this singular toric threefold admits a non-rational form of the ground field. So the twist that's necessary, so we're blowing up points in P3, 4 points in P3 to get there. So there is an S4 acting on the 4 points. But also there is a Cremona transformation. So if you look at any Z2 in the S4, together with the Cremona transformation, if you make this your Galois twist, you're going to pick up non-trivial H1, you're going to pick up an abstraction to rationality of the torus. So, in other words, using specialization to a singular toric variety that's not rational, we can also show that, let's say, intersection of two quadrics is unrational. Which brings me to you guys. You like to degenerate Fano varieties to toric, not only Fanos, to toric varieties, threefold, fourfold, because you like to understand things in the toric limit somehow. And so an arithmetic application would be to do this equivariantly with an action of a finite group, so that in the limit, what we're seeing is a toric variety with non-trivial H1, which is just non-trivial H1 for the action of the characters of the torus. And you don't need much to pick up that thing. You just need Z2 plus Z2 in dimension 3. And, well, then you get a supply of non-rational with the ground field, but geometrically rational varieties. Thanks a lot. Thank you.
So, are there any questions? Everything is clear. Thank you very much.